So it's a pleasure to introduce Umberto Hryniewicz from Aachen, and he will talk about the Hofer-Wysocki-Zehnder conjecture for Reeb flows on a tight 3-sphere.
Thank you, Leonardo, for... Is the mic on? Yeah, okay. Thank you very much for the invitation, for the opportunity to participate again in the workshop. Really means a lot to me. I'm going to talk about joint work with Ben Cristoforo Gardner, Michael Hutchins, and Hui Liu. So the main result is concerns the dynamics of a contact form on M close connected 3 manifold. All right, so I'm going to try to state 2 results. First result, if there are exactly 2 periodic Hebb orbits, say lambda Hebb orbits, then C, here C is the associated contact structure. This becomes a symplectic vector bundle with to form d lambda. So MC is a universally tight plane space or 3-sphere. I guess I should say just sphere. Periodic orbits are irrationally elliptic and actions and Conley-Zehnder indices of the periodic orbits. Here I mean, of course, periodic Hebb orbits behave exactly like in the case of irrational ellipsoids. So including relation to the volume, resonance relations, etc. So any quantity which has symplectic meaning behaves just like in the rational ellipsoid. And dynamics is described by irrational rotations on disk-like global surfaces of section. So that's what happens if there are exactly two orbits. And then the second part of the theorem asserts that if the first joint class of the symplectic vector bundle is torsion, then there are exactly two or infinitely many periodic orbits. Okay, this second part implies a conjecture by Hofer-Wysocki-Zehnder asserting that two infinitely dichotomy holds for type 3 sphere. So for Hebb flows with a type 3 sphere. So this conjecture.
Sorry, but what do you mean more precisely with irrational rotations or this like global surface of sections?
So the two periodic orbits, either they both bind disk-like global surface sections, and the return map is an irrational rotation.
But you mean the return map?
Yeah. Sorry.
Yeah, that's not good.
Pseudo rotation. Pseudo rotation. All right. Sorry about that. Any more questions? All right. So this conjecture was upgraded. I mean, in the community, this conjecture was upgraded to a conjecture about the two infinitely many dichotomy for periodic orbits for any Hebb flow on a three manifold, on a closed three manifold, connected. I think until very recently, this conjecture never appeared in the literature. So two infinity conjecture. The same holds for any Hebb flow on a closed connected three manifold. So Hofer-Wysocki-Zehnder proved this for the type 3 sphere, assuming a little bit more non-degeneracy. So assuming a little bit more genericity. Hebb flow, they proved the conjecture when the case, for the case when the Hebb flow is non-degenerate, in the sense that periodic orbits are non-degenerate, and you have transversality between stable and stable manifolds of periodic hyperbolic orbits. And there is a this conjecture was, so in the non-degenerate case, you have a result by Collin, de Hornoy, Hertmann. So two infinite conjecture holds for when the contact form is non-degenerate. So that was a result so far obtained in this direction. Here, the novelty here is to remove the non-degeneracy assumption. All right, so a bit in the spirit of what Michael said in the beginning of his talk, what can be said about flows without genericity assumptions? All right. So corollary. If the first trend class is torsion, then a hyperbolic periodic orbit forces infinitely many periodic orbits. That's one corollary. Second corollary, Finsler geodesic flows, Finsler metrics on S2 have exactly 2 or infinitely many closed geodesics. That's because the unit tangent bundle of S2 is length space. So this torsion assumption is for free. And so in particular here, another proof of the result by Victor Bangert and John Franks on the existence of infinitely many closed geodesics for Riemann metrics on S2. Okay. I'll try to say something about the proof. Any questions about the statements? So the proof is based. So the proof is, as usual, done by perturbing the flow to a generic situation, getting some conclusions about the perturbation, and trying to pass the conclusions to the limit as this perturbed flow is converging back to the original flow. So here is a proposition. So again, our M is a closed connected three-manifold. So assume you have finitely many periodic lambda have orbits. Assume also, C1 distortion. And assume assume eta is a positive number, then there is a sequence there is a sequence of objects lambda n, j n, gamma n plus minus, u tilde n. So here, so lambda n is Gn times lambda. Gn is a function, is a smooth function converging C infinity to constant function 1. For every gamma periodic lambda have orbits, Gn respect to gamma is 1, dGn respect to gamma is 0. Okay. In particular, these finitely many periodic lambda Hebb orbits are also periodic lambda Hebb orbits of the perturbation with the same action. You have Jn. These are symplectization type almost complex structures on symplectization on R cross M. They converge to some limit, which is also symplectization type almost complex structure. These guys are say, adapted to lambda n. This means that it preserves the contact structure, positive with respect to d lambda, and sends vertical direction to Hebb direction. The limit here is also adapted to the limiting contact form lambda. Gamma n plus minus. So these are periodic lambda n Hebb orbits. Not necessarily multiply covert. They converge. They have action bound, so they converge to some periodic lambda Hebb orbits. The UN, these are finite Hofer energy. So they have finite energy cylinders. So one positive puncture, asymptotic to gamma n plus, one negative puncture, asymptotic to gamma n minus. The lambda areas are bounded from above by this number eta, which can be taken arbitrarily since the beginning. And right, so the index, the Fredholm index, and also the ECH index. So I have to, the proof is based on ECH. So this is the, I have to maybe a bit, if I have time, explain what these quantities are. These are equal to 2.
So these orbits, gamma n plus minus, they are non-degenerate.
Yes, the lambda n are non-degenerate.
Lambda n is non-degenerate.
Right. They are, I didn't say that, I guess. So lambda n, no, sorry, yeah. These are non-degenerate approximation. So the So this a periodic orbit always has a rotation number, transverse rotation number, which is well defined modulo 1. So the rotation numbers, so rotation number gamma n plus is strictly between 1 minus 1/2 and 0, modulo 1. And the rotation number gamma n plus is strictly between 0 and 1/2. This is all modulo 1. Cool, so that's the main technical proposition. And the proof of this proposition uses ECH, embedded contact homology, as introduced by Michael Hutchins. And it's very technical. That's all I can say about this proposition. But I'll come back to it at the end of the talk if I have some time. The what, sorry?
The error of this number is going to be the difference between the integral of lambda
This?
of the orbits.
Right.
And then you will be converting the difference between the action of lambda plus and gamma minus.
Right.
How can you take the eta to be arbitrary in that sense? And still,
So what's the question?
because from what I understand, you first fix an eta. Suppose that I took this eta that's smaller than the difference between the actions of the two orbits that we started with.
Right, yes. So for instance, the good thing is if you take eta, no, this is not existent eta. This is let eta be given. Eta is a input of, so I give a eta, you give me an eta, I give conclusion, you have these cylinders. Not exist an eta, it's let eta. Yes, finitely many periodic orbits, yes.
So then, well, let's assume there's two. Do you allow the gamma minus to be equal to the gamma plus or something like that?
So
There's two and then they take the eta is more than
maybe I answer your question by saying that also this is positive.
oh,
They are not necessarily multiply covered. Like in any rational,
they can be multiple.
yeah, actually there will be eventually, yeah. So in particular, if eta is very small, like like a tiny little number, this implies these orbits are geometrically distinct, for instance. Right? Because if they would be geometrically equal, no, but is there a question?
No, I'm good. There was a question.
Right. So here, this number is actually positive. I forgot to say that here. All right, so if you take eta like tiny, then, for instance, you have these orbits are geometrically distinct and so on. Okay, so now this orbit, so I'm going to work now under this assumption here. Then this tiny number depends only on lambda. So if this is, then you take a sequence of these cylinders, right? You want to study the limits. There's no space for bubbling off, actually. So, and the limiting has to be non-constant because I have a lower bound for the integral of lambda on a slice. So there is a limit. Okay, so claim the integral is positive. If it was 0, I mean, this number is between 0 and this tiny number. If it was 0, this will be converged to a trivial cylinder, right? But these are cylinders going asymptotic to orbits which are geometrically distinct, to have only finitely many orbits. You could slide up and down, make sure these cylinders go through a point, not in a periodic orbit. If that number was 0, this would be a trivial cylinder over a periodic orbit, going through a point, not in a periodic orbit. That's a contradiction. So this is positive. All right, so now okay. So what do you want to make sure? Maybe I forgot to say a very important thing here. So the UK projects to, that's not a consequence of the left. So this is like a continuation of the proposition. They project to Birkhoff sections for lambda n half flow. So there are many concepts. I mean, this comes from the fact that these moduli spaces are compact, so the dynamics sort of goes around in this moduli space. And the moduli space being compact is able to push the dynamics around, have a global surface of section. You might be worried about orbits getting stuck at the asymptotic limits, but this doesn't happen because of careful analysis. I mean, this has to do with partition conditions in ECH. You have to study them. And because these numbers, mod 1, are not 0, we can be sure that the dynamics also goes around the binding orbit, so it's a global surface of section. OK, so I'll try to come back to this proof of the proposition later. OK, so now let's study the situation in the positive puncture. So right, here is 0 in the real line. 0 is not in the spectrum of the asymptotic operator at the positive puncture, right? And you can show that, let's say, an plus minus asymptotic operators, meaning the hashing of the action function at positive negative punctures. Then you have a mu n plus minus asymptotic E values of the curves. They, for instance, the positive puncture, these are negative eigenvalues. They have a certain winding numbers. And you can show that's actually extremal, meaning it's the first winding number you see below 0. That comes from the fact that these are not positive hyperbolics, have constraints on the rotation numbers, and the index is 2. Same thing holds at the negative punctures. Same thing holds at the negative punctures. So here is 0. You have, so here is mu and plus negative punctures. They have a winding number with respect to any fixed trivialization. It's always the extremal winding number right above. So these asymptotic operators converge to the asymptotic operators of the plus minus periodic orbits. The mu n converge to asymptotic eigenvalues. And what we'd like to say is that this limiting cylinder has a good asymptotic formula. This is a degenerate situation. The cylinder, finite energy cylinder for degenerate contact form. You'd like to show the asymptotic limits exist. You have a good asymptotic formula. The exponential rate of decay is determined by the eigenvalues of the Hessian, just like in the non-degenerate case. That's what we'd like to show. So you have, now I'm going to talk about rotation numbers, positive, negative punctures. I'm going to talk about real rotation numbers with respect to the same trivialization I'm talking about when I talk about winding numbers here. Okay. The winding number is monotone with respect to eigenvalue. So, and also satisfy, for instance, let's say the assumption, the situation, the positive puncture. It's always below the winding number is always below the rotation number, right? If gamma plus non-degenerates, then, so, for instance, mu plus is negative, and you have a spectral gap. In the limiting situation, you have a spectral gap here. That's minus delta. You find a spectral gap where these eigenvalues are not touching this gap. Spectral gap. Gamma plus degenerates, then rotation number is an integer. Okay? Rotation number is, so you can also say the theta n plus minus converges to the rotation numbers of the degenerate flow. This is an integer in the degenerate case. So this guy is the winding number of the eigenvalue 0 because it's becoming degenerate. 0 now is an eigenvalue. But because these rotation numbers are below 0, you can conclude that by the proposition, you can conclude that theta n plus is less than theta plus, which means that the winding number of mu n plus is less or equal than theta plus minus 1, because these are integers, right? This integer is less than this one is less than that one. So now you take the limits. The winding number of this positive eigenvalue is less or equal theta plus minus 1, right? And theta plus is the winding number of 0. If the winding number of this eigenvalue is less than the winding number of 0, this means the winding number, the eigenvalue is not 0. This means you have a spectral gap. Spectral gap, again. So this means you can put exponential weights and hope for this curve to be in the moduli space with exponential weights and hope that, and now if that's true actually, then you can use them just like before. But of course now we have to prove that these curves, the limiting curve, limiting cylinder, actually converges to these guys, right? I mean, Y has asymptotic limits in gamma plus minus, and Y nice asymptotic formula. Actually, the proof goes back to Hofer-Wysocki-Zehnder. You have to modify this a little bit, has some refinements of this proof for these two facts. That we need is contained in the work of Pedro and I in many papers. So basically, you have a sequence of, you have an isolated critical point, have a sequence of Morse trajectories. They're coming in with a spectral gap. The critical point is degenerate. Zero is an eigenvalue of the Hessian, but they're coming in, Morse trajectories are coming in there with an exponential weight. So you can pass through the limit, you get a non-honest Morse trajectory going there with the same exponential weight. Now you cannot do Fredholm theory. This is a degenerate situation. But if you cut the weight, you do a weighted Fredholm theory, same Fredholm theory as before. So that's what's going on here. So that part I'm not explaining, right? So have to control the ends. Definitely the assumption that there are finitely many periodic orbits is used here. Okay, so now once you have this nice, now you have a moduli space. Let me denote it like this. It's M, J, say delta for the exponential weight, gamma plus, gamma minus. So holomorphic cylinders modulo reparametrizations, modulo translation in R direction, asymptotic gamma plus, gamma minus. We just found one. We did a little bit, I showed a little bit of the analysis of the spectral gaps, then one can plug in the analysis here and find that these cylinders, this moduli space, is non-empty. Okay? The index is again, right? I have to put an index with exponential weight, is the limit of these indices, again 2. So this means that the moduli space is one-dimensional, because you mod out by R translations. Very low action difference, but very high action. Actually, it turns out these orbits are very high iterates. I mean, don't know how high these iterates are, but they are high iterates. There are also orbits, as you cross, they have special property. As you cross the number delta in the real line, the eigenvalues of the positive punctures, they jump in winding. And also if they cross the number, minus delta on the positive puncture. If you cross the number delta and the negative puncture, the eigenvalues jump in wind of the Hessian of the action function. So these were limits of Birkhoff sections, because that's what's happening here. Right? So now you use this fact. So there is a technical argument here. Just explain the structure of the arguments. To use the fact that this cylinder maps to R cross the complement of these orbits. Okay? So if I write in two components, so I'm saying that the M component maps to the complements. Then you can also show that periodic orbits in the complements intersect the holomorphic, the projection positively. You can also show that U of a loop in the domain of U, beta is a loop in the domain of U, the image intersects 0 the map U. So many properties of Birkhoff sections, like they're embedded. Take a loop, intersection number with the surface itself is 0. Take periodic orbit in the complement, intersection number with the surface is positive. They share some properties of the Birkhoff section. We'd like to say this is a Birkhoff section. We cannot do that. Also, we'd like to say this moduli space is compact. That we can do. So why is the moduli space compact? Because of this linking assumption. If it's not compact, by the way, you cannot use SFT compactness, right? You can do compactness. You have to do compactness a la the 90s, right? So you have to really do compactness. There is no, the contact form is not non-degenerate. But still, modular space is not compact. By the way, have automatic transversality. Modular space is a one-dimensional manifold. If modular space is not compact, it's going to break into orbits. These orbits have to intersect, right? The class of the cylinder U again, and I get a contradiction. So have compactness of the modular space. So finally, you have this modular space, M. Now you consider the modular space with one marked point. So the dimension, this M here is the modular space over there. This is 1. When I say the modular space compact, now I'm restricting to the connected component of this map. Right? Forget about the rest. Just think about the connected component of this map. It's a circle. It's a compact one-dimensional manifold. It's a circle. If you put a marked point, now you get these 3 manifolds are solid torus, right? I mean, it's a fibration over this circle, and the fibers are planes. Sorry, not solid torus. It's a nullus cross interval, a nullus cross circle. These are annuli. Base is a circle, fibers are annuli. So a nullus cross circle or torus cross interval. Okay. You have an evaluation map. Evaluation map. Just evaluating the marked point. Takes values that complement the periodic orbits. Okay. So the what we'd like to do is to show that the evaluation map is a proper local diffuse. So local diffuse, it's not so complicated. These curves, because of all the index constraints, these curves are transverse, immersions transverse to the Hep flow. You have to analyze a bit the tangent space and so on and show that the evaluation map has, you know, it's a non-singular 3x3 matrix. Properness comes from the fact that if the evaluation map is converging to a point, this point, the corresponding holomorphic curves also have to converge. I mean, just you have to analyze a bit what's going on. You take a pre-image of a a sequence of points converge to a point in the complement of gamma plus, gamma minus, take the pre-images. Where is and then you fix parametrizations, and you have to say, where is the marked point going? The marked point is mapped by the evaluation mapping to those points which are convergent to some point. Where are the marked points going? Can they escape? Can they escape to the ends? Or do they have to converge in the domain, in the cylinder? And the question, the answer is, basically, the analysis one does here, one gets a uniform control of what's happening in the ends of these moduli space. So you can show that once you fix parametrization on a sequence, uniformly, you can be sure that the fixed end of the cylinder is mapped to a fixed small or a tubular neighborhood of these orbits. So marked point cannot escape to the end, otherwise you'll be converging to an orbit, but one of these orbits, but it's not converging, so proper. Proper local diffuse. So what we can do now is lift Hebb flow via the evaluation map to flow on the moduli space with one marked point. The Hebb flow is, because these curves are transverse to the Hebb flow, when you lift the Hebb flow, the flow here is transverse to the fibers of this. That's the forgetful projection, right? The forgetful projection here, it's transverse to the fibers of this map. So you have circle cross annulus, a flow which is transverse to these annulus-like pages on this modular space. And basically now you really you would like to say that these annulus-like pages here are global surface of section for the lifted flow, and they are, because one has to show this, of course, but because these guys come from Birkhoff sections of the perturbed system, and you have these erased here. Property of the rotation numbers is controlling what's happening to the binding, so you show that trajectories don't get stuck in this non-compact space. They really go around via this projection here. So I have a global surface section here and here. So final step, evaluation map is proper. If you have finitely many orbits here, right, and we are under this assumption, because the evaluation map is proper, if you lift an orbit here, you get finitely many periodic orbits there. You're not allowed, it doesn't happen that you lift a periodic orbit here, get some crazy orbit there. Because of properness of the map. You lift a periodic orbit here to a periodic orbit here, and only to finitely many. If you have finitely many periodic orbits here, by properness of this map has also finitely many periodic orbits. But the flow here has an annulus-like global surface section. By Franck's result, you either have none or you have infinitely many. So also here, the flow in the complement of these two orbits either has none or infinitely many periodic orbits, and that's the end. So we have to apply John Franck's. To lifted flow. Okay, so that's the rough sketch of the proof. Maybe one can prove directly. Maybe one doesn't need this lifting procedure. One can prove directly that these guys are global surfaces of section, but we couldn't. So I have like 11 minutes. So the sketch of the proof is finished. I mean, modulo the proposition, of course. Okay, so what about the proof of superposition? So the proof uses ECH and asymptotic volume formula for spectral invariance coming from ECH. Okay. So basically, and that the proof uses this torsion assumption. One looks at these towers of curves counted by the U map in ECH so that the actions of the asymptotic orbits are recovering the volume by the so-called Weyl law. And one has to show that this is a argument. Of course, the seed of this argument is in Pomeliano, Hutchins, and Christopher Gardner's paper for the non-degenerate case. Have to show that most of these orbits have control on the topology. This is controlled by what in ECH people call the J0 index. If the J0, so most of these orbits, most of these holomorphic curves counted by the U map in this tower, coming from the asymptotic volume formula, they have G0 index equal to 2. That's not quite enough to show they are cylinders. One has to introduce a different number associated to these orbits. In our paper, it's called the score of an orb, of a holomorphic curve. And you have to show that also most of the, for the orbits, for the holomorphic curves in this tower, the score, whatever it is, being 0, is enough to say these are cylinders. And also has to prove that most of these curves have score 0. So eventually there's a very complicated argument using so-called score. Basically, you want to show many of these curves are cylinders, under the assumption there are finitely many orbits. The assumption that there are finitely many orbits is used all the time. And the torsion assumption comes in when one wants to study relations between Koenig-Zehnder index and action. If you want to study relations between Koenig-Zehnder indices and action, you're lost if you don't have some kind of control on the Chern class. And actually, so one works with the homology class of the asymptotic limits of the ECH curves. They are in 0 homology class. So asymptotic limits 0 in H1, right? And because if you want to use also that these are 0 in H1, you better have torsion, because if you don't have torsion, you cannot use this homology class in the orbit sets which come from ECH. So summarizing, complicated arguments. But the arguments, I'll take the last 8 minutes, argument can be simplified if we understand the following problem. So very basic problem. You have a function on Rn, say the only critical point is the origin, say. All right? Say just one critical point. Function on Rn with one critical point. Okay. Can f be perturbed to Morse function f plus, I don't know, delta, so that the number of critical points which bifurcates from 0 is controlled. And by controlled, I mean I would like to get, so here, the perturbation is C infinity small, and I'd like to say I have a control the number of critical points which bifurcate, and the control is independent of this perturbation. Tiny special case, which is also very hard, and I think it's also a fundamental question that, right. Right. So, simple question, but also fundamental. Fundamental for, I guess, life in general. So suppose local Morse homology is 0. Can isolated critical points be perturbed away? By that I mean no bifurcating periodic points. If you answer this question, I mean, roughly speaking, you're also answering equivalently the same question. Fixed point of area preserving map, isolated, local homology, let's say Floer or Morse, 0. Can you destroy the fixed point? Okay, I think it's a pretty fundamental question. It's amazing we don't know the answer. So I'm just going to finish with result collaboration between so Urs Fuchs, Daisy Lima, Katy de Rezende, Mariana Rodrigues, yes, if dimension is equal to 2 or to 3. So, for instance,
Then in this case, what's the bound?
yeah, this is a special case, right? I mean, you'd like to have this bound based in terms of local Morse homology.
Yes, yes. But my question is, what is the bound in terms of the local homology?
You'd like to say it's maybe the rank of local Morse homology.
It's really the rank of
Yeah. So, of course, this is not a topology problem. If you put C0 here, it's quite easy. If you put C1 here, it's still easy. Because if you put C0, C1, this is still a topology problem. If you put C infinity here, it becomes a very, very tricky analysis problem. So here actually we'll have also preliminary result, yes, if a function is real analytic. So this bound, in the special case where the local Morse homology is 0, is that theorem over there. This is maybe folklore, not written anywhere. If you ask people, people say, okay, I can do this. This here, I thought it was surprising. Actually, we started by trying to disprove this. I mean, it's got to be a counterexample to this in dimension 3. And we ended up proving the result. Actually, more specifically, behind this theorem said that the Conley index under this assumption is a wedge sum, is always a wedge sum of spheres. That's the main, it's the analysis of the Conley index. That's the main result, implies that one. So I think this is a, and if we start getting answers to questions like this, for instance, for real analytic contact forms, the proof of the two infinitely many conjecture becomes really, really more simple because of this answer.
So, sorry, so then the bound is the total rank of the local model?
Hopefully.
You didn't prove this?
Yeah, but we prove in that case.
Yeah, that's true, yeah. We're talking about that case. So in dimension 2 and 3, the bound is the total rank?
No, I'm saying we proved in the case where the homology vanishes. So you see 0, and then you also 0.
You proved that's this one?
Exactly.
You didn't prove
Special case where, so you want, hopefully you have a number.
This one is still open even in low dimension?
Right, you have a number, you don't know what it is. Maybe a rank of local Marshall model. If it's 0, what this would be saying, you can perturb it away. And that's what the result is saying over there. So I'm probably going to stop here. Thank you.